Okay, let's continue with ensemble methods. So far in this course, we have only studied single classifiers. So basically the approach is we take a set of training data, we learn either the probabilistic distributions of the features and the samples, or we learn a decision tree based on the features that reach out to leaves that have the labels, or we learn linear regression, or we learn a logistic regression. Okay, but it's just one way of learning labels out of the features that we have and using it as a classifier. What ensemble methods are a novel idea in the sense that instead of just being one classifier, they are based on a set of multiple classifiers. And the idea is that by combining multiple classifiers, we'll be able to improve the final accuracy of the overall classifier. Okay? In the sense that whenever we use the classifier on testing data, the final label that is assigned, instead of being assigned just based on the output of one single classifier, we're going to use the output of several classifiers and combine it to predict the final label. How we combine it depends on the type of ensemble methods we talk about. So we'll be talking about boosting, bagging, and random forests. But the idea is that each classifier is going to have a strength, and that strength is going to be taken into account for the final decision. Ensemble methods in general have been proved to improve single classifier approaches for many problems. So I'm just going to give you one example that used an ensemble classifier, which is the Netflix challenge. And it's a good example of how putting together different classifiers can heavily improve the accuracy of an approach. So the Netflix prize basically offered $1 million for any person who could improve their baseline recommender system. So Netflix at the time had a recommender system, and they wanted to get improvements of approximately 10% over their baseline. Okay, this is a supervised task, as you can imagine. I mean, now that you have already defined your project, you know that in this case we have different users, and each user is going to have a set of movies that have a rating from 1 to 5. So basically you want to use those users that have watched different movies to train a model that then will be able to determine whether an individual that has not watched movie X will like movie X. Okay. As I was saying before, Netflix already had a recommender system in place, and they wanted to see whether anyone could implement determining the correct rating for a given unseen movie. They could improve that by approximately 10% or more. What I'm showing here are the leaderboards from the competition. So this is the leaderboard just around 3 weeks after the challenge started. You can see the team name, the best score, and the improvement. The improvement column is basically that column is where we need to see a 10%. Okay, or we need to see something higher than 1%. That's basically in terms of the accuracy of the algorithm. What's the improvement with respect to Netflix classifier? How much is the approach of a given team improving a Netflix recommender system? So you can see here, the initial step, approximately the improvements for some teams, the top teams, was approximately for 5%. And suddenly, at some point, the Belcourt team presented an improvement of 8.5%. And this is where we can start looking into what were the teams talking about, what exactly were the methods that the teams were using for that huge improvement to happen. Okay, like initially the teams had around a 5%, but then suddenly now we are seeing 6, 7, and 8%. What's going on? If we take a look at the descriptions of the approaches that the teams were taking, basically, for example, this is just one team. They said, thanks to Paul Harrison's collaboration, a simple mix of our solutions improved our result. Okay, so this is an informal way of defining ensemble methods. They just combined two different classifiers and used the output as the final output of their classifier. This is just yet another team, and basically they more specifically talk about combining the results of many methods using a linear regression. Okay, so in this case they used a linear regression, and each element, each feature in the linear regression was actually one classifier. So what this means is that they were literally assigning different weights to different classifiers. And they can also, based on those weights, you can also figure out which one is the most important method. In this case, for example, they mentioned that the regularized SVD was the best method. Another team, ML at University of Toronto, they also describe how they were using multiple RVMs and multiple SVD smalls linearly combined. Okay, so again, this is a linear combination where each classifier is given a weight based on you know how well does it contribute with respect to the target class. And the final team, which was actually the winner team, Belcore team, they were researchers from AT&T Research, and they described that their final solution consisted of a blending of 107 different classifiers. Okay, so this is just to confirm the fact that there was a sudden, very large improvement in or with respect to Netflix baseline recommender system, and that was mostly due to the fact that people started using ensemble methods. And the winner, in fact, was Belcore's team with an improvement of 10.06%. Okay, so they actually managed to accomplish Netflix challenge, and they were the winners. What's the general idea? Now that we understand, that what are ensembles and an example in real life of how ensembles actually worked out pretty well, the general idea of an ensemble is that we have a training data that we divide into subsets of data, or different ways of dividing the original training data into different subsets, which can be the size of the original dataset, as we will see afterwards when we describe the specifics about each type of ensemble method. But let's say that we have training data and we divide it into different sets of training data. And on each set of training data, we apply a different classifier. And then finally, the output label or hypothesis, that H stands for hypothesis, the final label in our classifier is given by a combination of the labels of each individual classifier. The idea behind ensemble methods is that we have a set of weak experts. So each of those classifiers basically specialize in sub part of the training data. So they are really good at predicting the label for a certain type of training data points versus others. So what an ensemble method does is that it balances the strength of each weak expert in such a way that the final label, the final accuracy is improved. So each individual classifier, the contribution is weighted, and that weight associated to the classifier, it's based on the conviction of the classifier giving that label, okay, on the accuracy of the classifier, given that not only on the accuracy of the classifier, but also on the precision of that classifier. How's the conviction for that classifier? Is the classifier absolutely sure that that's the correct label, or is it just an approximation? Is it a 50%, 50%? So that conviction there is defined by the weight that we associate to the classifier. Talking specifically in classifiers, we could talk about the confidence value for that classifier. Okay, so a classifier will output a label, but with how much confidence. So that's also a way of understanding what the weight is. Ensemble classifiers, they have several advantages. They typically improve the predictive performance of just using one classifier. They're very easy to implement, and there's not much parameter tuning. So it's just if we are combining different classifiers, what's the weight that we assign to each classifier? But on the contrary, it has one major disadvantage, and is the fact that it's not transparent. So for example, when we saw decision trees, the way a decision tree works, the way it's trained, the way the decisions are made is pretty obvious, whereas for ensemble classifiers, the classifier in itself is not as transparent. And again, ensemble methods probably work because if you look at different, for example, human decision-making processes in which independent opinions are combined, or you seek the opinion from different experts to finally take a final decision, or if you think, for example, about how people manage their stock portfolios, instead of just putting all their money into one value, they decide to diversify that. So basically, that's the way an ensemble method works. Rather than just focusing on one single classifier, why not just ask different experts, ask different classifiers that might be good at assigning a label to different types of samples in a given dataset. And finally, it's just another, again, a last intuition before we start, looking into different types of ensemble classifiers. Imagine that you have, for example, 5 completely independent classifiers, right? And the accuracy for each of those classifiers is 70%. If imagine that we combine, okay, I mean, individually their accuracy is 70%, but if we combine those 5 independent classifiers, okay, what can happen for any given sample is that either the classification is correct for all of the 5 classifiers, either the classification is correct for 4 classifiers but incorrect for 1, or either the classification is correct for 3 classifiers but incorrect for 2. Okay, those are the 3 different scenarios that can happen. So what that formula is showing, the 10 by 0.7 to the 3 multiplied by 0.3 to the 2 plus 5 and so on. So what that formula is representing is what are the different scenarios that we could have as output labels based on a combination of 5 independent classifiers. So if we were to have 5 classifiers and based on whether the final label is correct or incorrect, what would be the accuracy of that ensemble classifier? Okay, and it's 83.7. So what this means is that by just putting together 5 classifiers that are completely independent, the accuracy can be boosted from 70% to 83.7%. And if instead of 5 we were to use 101 different classifiers, okay, what that formula there is showing is the number of different combinations that we could do of the classifier being correct or not, the output of the classifier being correct or not. And so with 101 such classifiers, the accuracy would be 99.9%. Of course, what happens is that typically, the accuracy of the individual classifiers is not as high, or oftentimes, the classifiers themselves are not completely independent. Okay, so that's a reason why not every time we combine 101 different classifiers, the accuracy is 99.9%. Unfortunately, that's not always the case. But it's just a way of understanding, the power that lies behind ensemble methods. And, I've been saying continuously that, we can divide the original training data set into different data sets. We can assign different weights to different weight classifiers. So the way different things are done differently depends on the type of ensemble method that we talk about. And I'm going to be talking about a couple of different methods, boosting methods and averaging methods. And in averaging methods, I'm going to be talking about bagging and random forests, which are very similar methods, but with slight change in how the features are used. So let's start with boosting. The idea again behind boosting is, can a set of weak learners create a single strong learner? Okay. A weak learner is a classifier which is only slightly correlated with the real label. And a strong learner is one that is very well correlated with a real label. So again, remember that the objective of building a classifier is that the labels that are outputted for the test data are correct in most of the cases. If the learner is weak, if you compute, the correlation between the real labels and the labels that your classifier outputs, if that correlation is high, the classifier is really good. If that correlation is low, the classifier is not that good. So that's what I mean by weak learner, lowly correlated, strong learner, highly correlated. The way boosting works is that given a weak learner, we run it multiple times on reweighted training data, and then we let the learned classifiers vote. What do I mean by this? So boosting is an iterative process, and in each iteration, what it's going to do is that it's going to assign a weight to every single sample in the training data, and the weight is going to be assigned correlated to how incorrectly that sample was classified with the previous classifier in the previous iteration. If the sample was incorrectly classified in the previous iteration, the learner, the classifier that we are going to build in this iteration is going to focus on those samples. So at each iteration, we build a classifier that's going to focus on correctly classifying the data points that were wrongly classified in the previous iteration. That's the classifier that we are learning at each iteration. Also called, in this case, we refer to the classifier as hypothesis, okay? But the hypothesis is just a weak learner that we are learning, and at each iteration, that learner is going to focus on the samples that were incorrectly classified. Once that weak learner is learned, the accuracy of that weak learner is used to compute a strength, and that strength is basically the importance that we give to that weak learner in the final assignment of a label. So once once we have gone through all the iterations, the way the label is finally assigned is by a linear combination of the votes of the different weak learners that we have learned, and each weak learner is going to be weighted by the strength of the classifier. Let's look at it mathematically, because sometimes it's easier to see it actually expressed in formulas than verbally. So what we see here is that given a set of data points where we have a feature and a label, the label is a binary label, -1 or +1. We create a set of d values, which are the weights. Originally, all the weights that we assign to each data point, initially all the weights have the same importance. If we have m different weights, 1 over m is the initial weight assigned to each of those. And basically we had an iterative process from 1 to t. And in that iterative process, what we do is that first thing, as I was saying, we train a weak learner using the distribution of weights. What this means is that basically we're going to we always work with the complete data set. We always work with all the training points, but we give different importance to those points. Okay? So basically what we do is that we're going to learn a hypothesis, we're going to learn a classifier, H, and we're going to compute the error. So for that hypothesis that we are learning, we compute the error, and the error again is, what's the probability, or how many times does it happen that the classifier's output label is different from the actual label that we have. That's exactly what it says when it says PR of HTXI different from YI. What that means is that the HTXI, meaning the label that your classifier assigns to the testing to the training data point, is different from the actual label that it has in the training data. Once we have computed that error is basically used to compute the strength. As I was saying before, we also compute a strength of the hypothesis, strength of the classifier, meaning that the better the accuracy or the smaller the error, the larger the strength that we give to that classifier is going to be. And then finally, we need to update the d values. As I was saying before, the samples that were incorrectly classified are given a larger weight, such that in the next iteration, the hypothesis is going to focus on those samples. And so once we have done these 3 points, at the end of the for loop, the final hypothesis is going to look like the capital HX that you see at the bottom of the slide. So basically, the final hypothesis, the final classifier, is going to be an ensemble, a summation of all the weak learners, of all the HT of X that we have, multiplied by their strength. The alpha T value that we have computed at each value of T in the loop. We basically compute the strength for the hypothesis, and those are the strengths that then we use to in the summation to basically add up the final label that each classifier outputs. Okay. If we are talking about a regression, that's simply as you see it there, it's going to be a summation of all the hypotheses multiplied by the strengths. If it's a classification problem, then it's a voting scheme. So it's going to vote for one or another one. So let's look at an example of how would that exactly work. Imagine that we have something like this. We have positive and negative samples, and we want to build a classifier. Initially, if we use an ensemble method, initially, the ensemble method will create a weak learner. And imagine that the weak learner is the red line that I'm showing here. And that weak learner is separating some positive samples from the negative samples. But in this case, we observe that there are 3 positive samples that lie within the negative sample area. So those are 3 errors that our weak classifier has made, right? So for this iteration, we compute the error of the classifier, but we also compute the strength of the classifier. And then what is it that we do? We recompute the weights of the samples, and the samples that were incorrectly classified, in this case the 3 positive samples, are given more importance. That's the reason why in D2, the space D2, that's the reason why I put there a larger, the positive signs are larger for 3 samples, because those are the samples where we are going to put, let's say, the importance to learn the next classifier in the next iteration. Okay, so now for iteration 2, which is the square in the middle, we learn yet another weak learner, another hypothesis, which is H2, which has the epsilon 2 error and the alpha 2 weight, strength, sorry. Okay, so in this case, what we see is that we are building yet another classifier, which in this case has put together all the positive samples, but we have 3 negative samples which are incorrectly placed because they are in the area of the positive samples. So in this case, as you can see in D3, what we observe is that the negative samples that were incorrectly classified are given more importance. So when we recompute the D values again, those D values are going to be larger in the third iteration because those 3 negative samples are the ones that were incorrectly classified. So in round 3, we learn yet another weak learner, and what that weak learner does is that it basically separates positive samples from negative samples, but there are 2 different types of errors in this case. In the positive area, there's 1 negative. In the negative area, there are 2 positives. So in this case, the distribution of weights is going to be such that both the negative sample and the 2 positive samples in the negative area are going to be emphasized. Okay? So in the end, we repeat this process, okay? If you can see here, the strengths were 0.42, 0.65, and 0.92. So these are, as you can see in the final hypothesis, these are the 3 weights that we use. And the squares there just represent the hypothesis that we have learned, the weak learner that we have learned, okay? I mean, that's going to be whatever model we have computed, that's going to be what's in there. Okay, so in the end, as you can see here, what each weak learner does is basically focus or specify or become an expert in a given subpart of the training data in such a way that each of them are experts at separating certain type of positive samples from certain type of negative samples. Okay, and by combining their localized or their focused expertise, we basically come up with a final learner that's better than the contribution by each individual learner. Let me show you yet another example of ensemble methods, and we're going to be using UCI benchmarks are just different types of data sets that you can use for their typical traditional data sets used for machine learning problems. And in this case, what I'm going to show is how a combination of different decision trees can actually help boost the results. Basically, what you see here is that originally the problem was solved using a 4.5 decision tree. That was a hypothesis, that was the model learned. But then boosting is applied to that benchmark. Okay, so what you can see here in the representation are the plot error rates. On the x-axis is boosting of the decision tree. On the y-axis is the decision tree itself. Okay, as you can see, the error rates are definitely larger for the decision tree than for the boosting approach. Okay, it becomes obvious that the error rates are much larger for just a single classifier than for when that classifier is boosted through a combination of several of them. Okay, again, that's emphasizing the same idea. What multiple classifiers do, what an ensemble method does, is that it allows to basically reduce the overall error, thus increasing the overall accuracy of the algorithm.